Good evening. I'm Spot On Weather meteorologist Matthew Euler, and tonight we're going to continue on our journey in the summer weather video training series, and we're going to talk about atmospheric motion. Very, very important. I have a couple diagrams here on the title slide tonight. The first image on the left with the blue arrows shows how the air can converge at the upper levels of the atmosphere. When I mean converge, all I'm saying is that the air is meeting, and as it meets, it works its way downward and forms descending air currents. And then at the surface, sometimes you get that air, once that descending air, that sinking air hits the surface, it spreads out horizontally, resulting in the divergence, or the spreading apart of air currents. In addition, the image on the left, on the right-hand portion of that image, shows a different situation in which you have the air meeting at the surface of the Earth. That's known as convergence, when the air currents meet. And when they meet, they have to go somewhere, so they go up in the atmosphere. That results in rising air currents, and ultimately you have this divergence of air above that low-level convergence, which removes mass, and we'll get much more into that. So this up and down motions in this three-dimensional atmosphere are very important. The image on the right just shows that divergence and convergence, the spreading apart of the air currents, the coming together of the air currents, in relation to surface pressure features, those low pressure areas, and the blue H, the high pressure areas. So a lot to talk about tonight, a very important topic, and let's get right into it. So the first thing we're going to talk about is divergence. Again, divergence refers to the spreading apart of air currents, or it's a measure of the rate of net removal. We're removing the mass. We're removing mass out of a volume of air above a given point, and what this results in is a decrease, a lowering of atmospheric mass above a given point in the atmosphere. So with divergence, spreading apart of air currents, the removal of mass, it can be caused either by speed changes or by directional changes, or even both at the same time. And I have some great diagrams in tonight's training on atmospheric motion that's going to show that. Okay, so here's the first diagram. This is showing you the effects of divergence, or the spreading apart of air currents. You see the image on the left, or the overall image here, of course, but the main portion on the left there shows the dashed line. That represents your level of non-divergence. We'll get into that here in a moment. But the first thing we're going to talk about is mass is removed from a given point. Now, that's the first thing. So, on the image on the left there, we have 1010 millibar surface pressure. We have a 500 millibar pressure surface. And then we have this airflow indicated by the arrow there, the big arrow. Now, as the arrow basically spreads apart into multiple pieces, it results in divergence, or that removal of mass above a given point. And you'll notice the image on the right, the little graphic on the right portion of this diagram, or the image, you'll notice how the 500 millibar surface has got lower. So the amount of mass above decreases, so the height of that 500 millibar surface also decreases. So when I have upper level divergence, or removal of mass aloft, the spreading apart of air currents, that's going to result in a lowering of my pressure surfaces. Because you have less mass above those points, that surface pressure therefore is going to drop. With convergence, on the other hand, this is when the two air currents come together. When air currents come together, we have what's known as convergence. It's a measure of the rate of the net addition or gain of mass into a volume above a given point. And with convergence, this is going to result in an increase of atmospheric mass above a given point. What you'll find a lot in meteorology is the equal and opposite effect. So for divergence, my air currents are spreading apart. I have a removal of mass above a given point. That will lower my surface pressures, or lower my surface pressure features. With convergence, which can also be caused by speed, direction, or both, and I'll show you what that looks like here in a minute, this is going to result in an increase of atmospheric mass above a given point, just the opposite effect of divergence. Here is an image showing you, a diagram showing the effects of convergence now. And what's happening, the image on the left shows the 500 millibar pressure surface. You see how the arrows are pointing towards each other on the left? That is showing how the air currents are coming together. They're meeting, they're coming together and converging. As the air converges, mass is added. As the mass is added, the surface pressures are going to rise. So if you look at this little tube type diagram, you'll notice the 500 millibar pressure surface in the image at number 2 is higher up, or that the isobaric pressure surface has actually risen. So that's the effects of convergence. With more mass above a point, the surface pressure is going to rise. Now, there will be some equations in tonight's training, but again, keep things simple. I'm not going to really delve too much into the equations. I'm just going to maybe show you, introduce you to a couple of the terms of the equation, but we will not be breaking down any kind of mathematical problems in the training. Higher speed, divergence equations, okay? Higher speed winds. We're talking about, so now as I mentioned, with divergence and convergence, those two atmospheric phenomena can be caused either by coming together or meeting of air currents or by speed, so by direction or speed. The first thing I'm going to talk about is divergence due to speed differences. So I want you to imagine up in the upper atmosphere at the jet stream level at about 30,000 to 40,000 feet above the ground, the wind is going to accelerate or decelerate, slow down in various regions of the main jet stream axis. And as a result, you're going to get areas that diverge, air currents that diverge due to that speed difference. And so when we talk about divergence, higher speed winds downstream pull mass out of an area faster than it can be replaced by slower speed winds, thus ideally decreasing the mass. Now, a good way to think of this is you're driving on the interstate, you're driving on the highway, you're in your car, and you're just leaving a toll booth. Because as you know, as you get to a toll booth, a lot of the cars, they really start stacking up. And I want you to imagine that you're driving in a car, and then you got done paying your toll booth fee. You paid for the toll booth to go through. The gate goes up, you hit the accelerator on the car, and you notice how bunched up the cars were before the toll booth, but now after you went through the toll booth, you start accelerating, and you'll notice all the cars that are way ahead of you already because they've already gone through the toll booth, and they are moving much further down the highway. So the cars are much farther apart. So the car, let's say 2 miles away after going through the toll booth, that car 2 miles down the road may be doing already 70 miles per hour on the interstate, whereas you're just coming out of the toll booth and you're only doing 10 to 15 miles per hour as you're accelerating. You're getting, you're going faster as with time, but it takes a little bit of time to get going again when you're pressing the accelerator, the gas pedal. So there's a lot of spreading apart of the cars. Same thing goes with air parcels in the atmosphere. You get these higher speed winds that are much further down that road or downstream, and they're pulling the mass out of the area faster than can be replaced by these slower speed winds or those slower moving cars. Thus that generally any kind of divergence is going to decrease that mass. Here's an example of speed divergence in the atmosphere. And this happens all the time in what we call jet maxes within the jet stream axis itself. We have regions of very fast flowing air, and we have regions of slower moving air in that jet stream axis, believe it or not. So the image here shows, the upper left-hand portion of it shows 20 knots in, 20 knots of wind speed into this area, 50 knots of wind speed out. So you can see the wind flow in this particular example was from the left to the right portion of the diagram, basically from a westerly direction. And you have wind speeds at 50 knots, much further downstream, 20 knots of wind speed is coming in. So therefore, mass is removed because that faster wind speed is downstream of your location. It's blowing out all those parcels through much quicker. And as a result, when you have any kind of divergence, look below the arrows. Divergence is going to lower your isobaric or constant pressure surfaces. So in this case, you see how the 500 millibar pressure surface drops. It gets lower, and as well as your surface pressure. See how you go from 1020 millibars in the atmospheric column down to 988 millibars. So divergence aloft is associated with rising air motion, lowering of your constant pressure surfaces, and this is usually, divergence aloft is usually a good indicator of storm development. The image on the right shows some wind barbs in an upper level chart. Each of the flags, one flag represents 50 knots of wind. The little half lines represent 5 knots. The full lines represent 10 knots. So if I were to look at the station in the upper right, I have two flags, two black flags, that's 100 knots. And then I have 1, 2, 3 full lines, which is 10 knots each, totaling 30 knots. So I have basically 130 knots of wind in the upper right-hand station plot. And then I go to the bottom left, I have 105 knots. So 130 knots is blowing downstream away from the area, and only 105 knots is coming in to replace it. That's an example on an atmospheric chart of speed divergence. Now, speed convergence, on the other hand, is caused by winds rapidly decreasing speed downstream. You have higher speed winds upstream pushing mass into an area faster than that mass can be removed by the slower speed winds downstream, and that's going to increase the mass. Okay. Here's a good example of this. We go back to that car analogy on the interstate. You're driving on the highway. Okay. Let's say you're about 3 miles. You see a sign that says toll booth coming up in 3 miles. Well, as you get closer to that 3-mile point where the toll booth is, you'll notice how the cars ahead of you are slowing down. So they're slowing down ahead of you. Maybe they're only doing, they're slowing down to 15, then to 10, then to 5 miles per hour. Maybe you're coming in at 60 miles per hour, and you'll notice how you slowly have to drop your speed to kind of merge in with that line as it goes to the toll booth. Same thing here with speed convergence. You have, in this case, cars ahead of you that are moving much slower, going much slower in speed than you are 3 miles away from that toll booth. So speed convergence, let's take a look at that. So now on the left, we have 50 knots of wind coming in, and we have 20 knots of wind going out. So you notice how the faster moving winds are eventually going to catch up to the slower moving winds, and that's going to add mass. It's going to add mass to the upper levels of the atmosphere. As the air converges, the air sinks once it meets. It's generally associated with high pressure at the surface. You'll notice the 500 millibar surface on this image, how it actually rises up or gets higher in the atmosphere. You notice the pressure changes all the way up to 1024 millibars. So surface pressure, usually speed convergence, any type of convergence in the upper levels of the atmosphere is associated with surface high pressure, sinking air motion, generally good weather. Now, if you look at the image on the right, showing you a slice of a weather chart, again, there's your wind barbs indicated by the various symbols. The dark flag is one of those is 50 knots. The half line is 5 knots. The full line is 10 knots. So in this case, if we compare these two stations, the wind barbs, we have 105 knots ahead of, basically downstream of 140 knots of wind. So the 140 knots of wind is blowing much quicker. Eventually, those parcels are going to catch up to the slower moving parcels ahead of them. That's going to result in accumulation of mass, sinking air motion, and ultimately your upper level heights, your constant pressure surfaces are going to start rising. Now, I mentioned about equations. Don't pay attention to the equations as much. We're going to keep this really simple. Just realize that there's two other terms. We just covered the speed aspects, speed divergence and speed convergence. Now we're going to talk about how mass is added or removed from an area due to what's known as confluence and diffluence. And this is directional, or I'll show you a graphic here as an example here in a minute, but this is the coming together of air currents due to wind direction. Okay, So confluence would be the merging of wind flow into a common axis point, and diffluence would be the spreading apart of wind flow from a common axis point. Let me show you what it looks like on this graphic. This is an example of what's known as confluent wind flow. So again, we're showing you what's known as wind barbs. In weather, we look at wind barbs in upper level charts. It helps us to determine what the wind speeds are, as well as the directions aloft in the upper levels of the atmosphere. So we have these dark solid lines. First of all, the dark solid lines on this particular graphic are your lines of equal geopotential height. They're basically your constant pressure surfaces. Again, the speeds for these wind barbs. If it's a solid triangle shape, it's 50 knots. One of these triangles, filled in darkened triangles, equals 50 knots of wind speed. If it's a full line, it's 10 knots. If it's a half line, it's 5 knots. So in this case, what we have is, I want you to pay attention to the left portion of the image. We have a northwesterly wind at the very top left. We have a westerly wind in the middle. And then at the bottom, on that bottom left, is showing you a southwesterly wind direction. So we have a merging of this wind along this common jet stream axis in between these height contours. And that's going to result in what's known as confluence, or the addition of mass above a given point. This is diffluent wind flow now. So you notice how my height contour lines, my solid lines, are spreading apart. That's a good indicator of diffluence in the atmosphere. You'll see that we have an upper right-hand portion. We have a southwest wind. In the middle, on the right, far right, we have a westerly wind. In the bottom right, we have a northwesterly wind. And so you notice these solid black lines kind of spread apart, and that's an indication of diffluence. If we were to look at, these equations with diffluence, just realize one thing here on this slide. Diffluence is a spreading or fanning out of wind flow or contours. And yes, that's a big fancy little equation there, right? But just realize, I just want you to take away the fact that diffluence may result in mass being removed from the area of diffluent flow. Here is an actual example of diffluent wind flow. Divergent wind flow removes mass from the column, because guess what? Your spreading apart of the air currents, again, is removal of mass. You can see that these blue little columns, slices in the atmosphere, the 500 millibar surface, which is about 18,000 feet above the ground, it actually will lower with any kind of diffluent flow. Diffluence is just a form of divergence due to wind direction, spreading apart of the winds. And you'll notice that diffluent wind flow is generally associated with removal of mass aloft, and generally a lowering of your constant pressure surfaces, lowering the upper level heights. On the image on the right, we take a chunk of a weather chart. We have a bunch of weather stations here plotted they're represented by those small little clear white circles. And we got a lot of wind direction. In this case, we got a strong wind direction from the southwest. In general, we have a fanning out of the height contours again, and that is indicated by the changing wind direction. With confluence, I just want you to take away one thing here. It's the merging of wind flow or contours, and it may result in mass being added to the area of the confluent flow. Here's an example of confluent wind flow. You can see on the left-hand portion of this image, the arrows, how they're pointing in towards a common axis point. You see the center arrow there on the left, how it's pretty much pointed to the right. You have an upper left arrow pointing towards that, and then a lower arrow pointed towards that. So there's a meeting of the wind along a common axis point. This is known as confluence. When you have confluence, you're adding mass to the column. Once you add mass in the upper levels of the atmosphere, the air sinks, the 500 millibar surface pressure surface rises, and also your surface pressure is going to rise because you have sinking air motion, which is going to increase that pressure at the surface. All right, so what we've covered so far is what is divergence, what is convergence in the upper levels of the atmosphere, what happens. Again, convergence is the spreading apart of the air currents. It's also the removal of mass. It can also be caused by wind speed changes, where you have faster moving parcels of air further downstream, right? So speed divergence is caused by winds rapidly increasing speed downstream. Again, higher speed winds pull mass out of the area faster than they can be replaced by slower speed winds, thus ideally decreasing the mass. And again, we already kind of covered this. These are very similar looking slides. We've kind of covered this already, so I'm not going to dwell too long on this again, but just realize I like to use my highway example because hopefully that kind of makes sense to you now with the highway example. You have cars 2 to 3 miles away from the toll booth. They've already paid their toll. They're well on their way 2 to 3 miles down the highway from where you're at, and they're going way, way faster than you are as you're just coming out of the toll booth. And so there's a lot of opening up or a lot of extra space in between cars in that case, and that results in the atmosphere, similar principle. We have faster moving air parcels, slower moving parcels coming in, but guess what? 50 knots is blowing out of that area. It's going to result in loss of mass and generally a lowering of that upper level height pressures, the geopotential height surfaces, as well as lowering of the surface pressure. Convergence caused by speed, again caused by winds rapidly decreasing speed downstream. Now you're approaching the toll booth. You'll notice how the cars kind of stack up and it becomes a line. Everybody's slowly crawling to go pay their toll. And this is what's known as convergence, right? I mean, you're not literally converging into the car ahead of you because that would be causing a wreck, but you're bunching up. There's a bunching up of those cars on the highway, and that's resulting in an addition of traffic, or an addition, if we're talking about the atmosphere, an addition of mass above a given point. Whenever you increase the upper level convergence, coming together of air currents, whether it be by speed or direction, you are going to result in downward vertical air motion, usually associated with high pressure. Okay? So there are cases now. I need to really go over this. There's actually cases in which the direction and the wind speed tend to offset each other on constant pressure charts. In general, the speed and direction, the wind speed and wind direction can either complement or oppose one another. So you may have a case, for example, here where you have speed divergence that's existing, where you have faster moving parcels downstream of your point in removal of mass, but that might be opposed by a negative effect of confluence, the coming together of the winds, the wind directions at a certain point along the axis. This could actually offset, these two terms could actually offset each other. Here's the example. How opposing effects of wind speed and direction can occur in the upper levels of the atmosphere. So the solid black lines again represent your lines of equal geopotential height. These are your upper level heights, okay? The solid black lines. So you see how that top one is labeled 540 decameters. The middle line is just straight across. Horizontal is 546 decameters. The bottom line kind of slopes upward, kind of like an upside, like upside down U. That's 552 decameters everywhere along that solid dark line. In this case, you'll notice how these height contours are getting closer together on the left-hand portion of this image. See how they kind of, these three lines get closer together on the left-hand portion of the image? So we have confluence on the left. All right, the winds are coming together. They're converging at a common axis point. So in this case, we have confluence, but look at your speed differences. Remember that the flags, the dark filled-in flag shapes, the triangle shapes, those represent 50 knots of wind. So if I were to position myself between the first set of wind barbs on the far left and the middle set of wind barbs there in the middle, if I were to draw a point in between those two wind barbs, okay, you can see there's 50 knots of wind in the center of this, and there's only 20 knots of wind on the far left. So I have speed divergence in this case, where the mass is being pulled out of an area much quicker than it could be replaced. So confluence, the merging of those solid height contours, those black lines, are getting closer together. Confluence is adding mass. And then speed divergence is removing mass. So guess what? Those two act equal and opposite to each other. They actually offset each other. The other example beneath that is where you can have confluence and speed convergence. And if you have confluence, you have the coming together, the tightening of those lines. They're getting closer together. That removes mass. And actually, that's not correct. Confluence should actually add mass, and speed convergence should add mass. So I apologize for the typo there. But anyway, the point here of this slide is you can get, on the right-hand portion, you can get diffluence where these height contours spread apart, and then you've got speed convergence where 50 knots of wind is blowing into 20 knots of wind. But either case, confluence plus speed divergence or diffluence plus speed convergence is going to yield opposite opposing effect. So what do we use in this case? There's other tools out there that can tell us, all right, if these offset each other, these forces offset each other, how do we know if the air is rising in the vertical or sinking in the vertical? Well, luckily for us, we have the vorticity charts and the vertical motion charts, which can indicate if you have net divergence or removal of mass, or net convergence or gaining of mass in the upper levels of the atmosphere. Okay, so these vorticity charts and these vertical motion charts are very useful tools for meteorologists to determine, hey, is my air rising, is my air sinking? Because if air is rising in the vertical, there's a good chance you got divergence aloft that is more dominant, and you're going to have low-level convergence, and most likely you can have stormy weather. Whereas if you have upper-level convergence, which is more dominant, you're going to have sinking air motion. As air sinks in the atmosphere, it dries and warms and results in fair or nice weather with high pressure at the surface. Sometimes the speed and direction complement each other, like I mentioned previously. There's therefore assessment of net convergence or divergence becomes more obvious. And we did cover vorticity on that last video if you want to take a look at that. All right, so I did mention this as well with what's known as ageostrophic flow. Very important in the upper levels of the atmosphere. This goes into more of the atmospheric dynamics. Ageostrophic literally means that forces are out of balance. And you take a look at my jet streams video. Take a look at the jet streams training video. I explain what goes on with ageostrophic wind flow, especially when we're talking about the level of the jet stream with those accelerated areas within the jet axis known as jet maxes. Ageostrophic wind flow means the balance of forces is disturbed. The atmosphere is seeking equilibrium or balance in all it does. In this case, ageostrophic is the vector difference between the real or observed wind and the geostrophic wind. And this difference will be in speed and or direction. The ageostrophic wind represents the divergent component of the wind. This is very, very important to atmospheric dynamics, especially in the upper levels of the atmosphere. This is going to yield areas of rising air motion and most likely developments of storms, and areas of sinking vertical air motion and high pressure, nice weather. So if I were to show you an example of an ageostrophic wind component, right? This particular diagram shows surface pressure. So we're at the ground level analyzing pressure. MB stands for millibars. It's just a unit of pressure. So at the top horizontal line, that solid dark line is 996 millibars. Anywhere along that line is a surface pressure of 996 millibars. The bottom of the image, I have a 1000 millibar area line. Anywhere along that line at the very bottom, the horizontal line has a pressure of 1000 millibars. Okay. We did talk a little bit about some of these forces that are involved when we go from high to low pressure. Again, as a refresher, everything in the atmosphere works from higher toward lower. Whether we talked about the formation of the clouds in that training video, or whether we talked about the laws of thermodynamics, where everything, when we have temperature differences of two substances, the energy is going to flow from the hotter substance toward the colder substance. In the atmosphere, we have this force that's called PGF, pressure gradient force, and that is directed from higher toward lower pressure. So if you notice on the graphic here, PGF, that arrow, I have a little air parcel there represented by that little blue, purple looking cube. And as the PGF arrow is going to point from basically to the left towards that 996 millibar isobar, or line of equal pressure. Okay, so you see the PGF is directed from higher to lower pressure because we have 1,000 millibars in the very bottom with that solid line. We have 996 millibars on top. All right, as the wind's blowing and we're at the surface, it's going to be disturbed. That wind flow is going to be disturbed by the force of friction, because what friction does is it acts opposite to the wind flow. So as an example, if you're out and about, if you ever notice the wind speed doesn't stay constant, you get what's known as wind gusts, because that airflow is disturbed. But on the surface, your winds are going to be much slower in speed too, though. They're going to be much slower in speed because the wind is blowing over perhaps a rougher area of land surface, or it's got to blow around, trees are slowing it down, houses are slowing down the wind speed. At the surface, you've got the force of friction. That's abbreviated FR in this example. And that's going to act to the left. The arrow pointed to the left there on the left-hand portion, that's FR, or friction. The arrow out ahead of that pointed to the right, from left to right, pointed that direction. That's your wind speed. Okay, so I have pressure gradient force basically pointing to the left of the wind's direction. I have friction going the opposite direction of the wind, and then I have this Coriolis force as well. Okay, and remember that Coriolis force is an apparent force in the northern hemisphere which causes objects, including the wind, to deflect to the right of its intended path. So all these forces, pressure gradient force, Coriolis force, frictional force, we temporarily have a ageostrophic wind component created now. That ageostrophic wind component is created because all these forces are not in balance with each other. The pressure gradient force, frictional force, and Coriolis force are out of balance. And you can see the arrow, the solid arrow from the cube there. That's my air parcel. It's basically pointed from the lower left, bottom left, towards the upper right. And that's going to be my overall ageostrophic wind. But you can see the dashed line of the arrow. The ageostrophic component is actually the difference between the wind direction parallel to these lines of equal pressure, the isobars, and what it actually is due to the out of balance forces with friction, pressure gradient force, and so on. So areas where there are significant ageostrophic or out of balance wind components, where do they exist? They exist in regions of strong curvature. This is going to produce variations in the gradient, what's known as a gradient wind speed, between regions of cyclonic, and I'll explain what subgeostrophic is here in a minute. Cyclonic areas generally have slower wind speeds, gradient winds, and that's known as subgeostrophic. So for that prefix sub, S-U-B, I want you to think of something like a submarine. Submarine goes under the ocean surface, below it. So when I mention the word sub, S-U-B as a prefix, that means the wind speeds are slower. All right, so in regions of strong curvature, which happens quite frequently when we're talking about long waves in the atmosphere, those long waves associated with the ridges and the troughs in the jet stream pattern, that's going to produce variations in the gradient wind speed between those regions of cyclonic turning of winds in the subgeostrophic area and those anticyclonic or the ridge areas, which is associated with super geostrophic flow. Now when I say the word super when I'm talking about winds, I want you to think of Superman. because Superman flies really high above the Earth's surface, okay? And if it's super, that means it's higher wind speeds. Superman flies high above the Earth's surface. So super geostrophic means to have area of very fast moving winds. And those are generally associated with the upper level long wave ridges at 300 millibars or 30,000 feet with the jet stream. Another area where you have ageostrophic wind components, where the wind forces are out of balance, is areas where there's friction. And that's generally in a layer, the lower atmosphere from the Earth's surface up to about 3,000 feet above the ground level. Okay, that's your friction layer. That's your planetary boundary layer is another way. It's another name for it. And what that does when you're dealing with surface highs and surface low pressure areas, just like this image shows, the winds are going to basically blow from higher to lower surface pressure at an angle across these isobars or lines of equal pressure. And ageostrophic or out of balance wind forces, they exist in regions where the wind is rapidly accelerating or speeding up or decelerating or slowing down. And this is going to produce variations in the actual wind itself, leading to a super gradient, remember super, faster, higher wind speeds, and subgradient wind flow, sub meaning lower. Okay. This is common, very common in the vicinity of jet maxes, and this has a lot to do with vertical air motion, whether it's rising or sinking, whether we have high pressure at the surface in nice weather or low pressure in storm development at the surface. So we have these divergence and convergent patterns. They're generated by this out of balance wind, this ageostrophic wind, which results in vertical displacements of the air. In other words, vertical air motion, which strongly influences cloud development and surface pressure patterns. Moving into one other topic here, it's known as mass continuity. What is mass continuity? Simply put, it states that mass can be neither created nor destroyed. It must remain constant in some form. So if I take mass and remove it from one region of the atmosphere, that mass lost must be replaced by mass from another surrounding area. Mass is conserved. That's mass continuity. So if mass is added to a region of the atmosphere, it must be redistributed to surrounding areas. I did mention this before when we talked about pressure systems. On that training video, we talked about the Chimney and the Damper effect. Due to the mass continuity and the conservation of mass, and basically what happens if you take mass away from one point, you got to replace it from somewhere else, or if you add mass in one point, it basically works both ways. In this case, when you have upper tropospheric divergence, so the troposphere is that layer, the first layer of the atmosphere that goes from the surface, extends well up into the upper atmosphere. Divergence in that particular layer, upper layers of the atmosphere, you're removing mass. It's known as a chimney effect. The removal of mass from the vertical column produces lower pressure at the surface. If you remove mass aloft via divergence, guess what? Mass continuity states that air you lose aloft has got to be replaced from the surrounding area. So what you get as the air is spread apart, the upper levels of the atmosphere, divergence is occurring in the upper levels of the troposphere, lower level air converges and vertical air motion results to replace that mass that's lost. So what you have is vertical air motion, rising air, and as the air rises, that's less force per unit area, and that's going to cause your surface pressure to fall. As the air rises in the vertical, air must come from somewhere else to replace that air as that's being lifted, and so you get this low-level converging air in the lower troposphere. This is usually associated with storm development, the chimney effect. What do you get when you have this happen? UVM simply stands for upward vertical motion. It's another way to say the air is rising in the vertical. You get adiabatic cooling. As air rises, it cools and expands. And the temperature of that air parcel is going to get lower and decrease as it rises. Eventually, that temperature of the parcel will equal the dew point temperature, and you'll get saturation and clouds to form. There you go, possible cloud and storm development and associated deteriorating weather as the stability changes. Your stability in this case is mostly going to decrease. There's a lot of factors involved with rising air motion. There's something known as latent heat, which is a hidden heat. As air rises and cools, and as it condenses, most importantly, and goes from a liquid to, or a vapor to a liquid and forms clouds, it actually releases heat to the surrounding air, which increases the instability. So there's a lot of things going on in the atmosphere here when we talk about divergence in the upper troposphere. Leads to rising vertical air motion, storm development, clouds, and upward vertical motion, adiabatic cooling. Here's the chimney effect shown in a diagram. So in this case, we have divergence aloft, but that divergence aloft is caused by speed changes. Again, there's wind barbs shown in the upper level of the lighter blue color. You'll notice you have 90 knot winds to the right, and to the left in the upper portion of the diagram, you only have 50 knot winds. So you have 90 knots of winds. It's like those highway cars again. The cars are way down the road from the toll booth. They're doing 70 miles an hour. You're just coming out of the toll booth only doing 10. So you have a lot of removal of mass here in this case, and divergence. Removal of mass due to that speed difference is going to, mass continuity states, I got to get that mass from somewhere else now in the atmosphere. So the air rises in the vertical, indicated by those upward arrows. It rises from the surface all the way up to that jet stream level at about 30,000 feet in the atmosphere. And that's going to result in clouds, upward, obviously the upward vertical motion is there, but clouds and storm development. You'll see the area of low pressure, the L, at the surface. The air is converging in the low levels of the atmosphere at the surface. Once it converges, it's got to go somewhere. It rises up. It's replacing the mass that's lost aloft. And that's known as a chimney effect. Here's what happens, the chimney effect, as far as actual sensible weather. You see that in this case we have wind barbs. So in this case we have diffluence where these dashed lines are spreading apart, they're getting further apart. That's removing mass in the upper portions of the atmosphere in this case, the upper portions of the diagram. You've got upper level divergence, the mass is removed, and mass continuity states that mass has got to be replaced by a surrounding area in the atmosphere to keep that mass conserved. So what you get is rising upward vertical motion of air. You get falling surface pressures. As the air rises, you have the adiabatic cooling via expansion, and you get showers and clouds. In this case, they're tall cumuliform clouds or cumulus clouds, those puffy ones. And they're generally showing a lot of instability, probably showery weather. You're getting a storm development in this case with the chimney effect. Now, upper tropospheric convergence is the opposite of the chimney effect. It's known as the damper effect. And with this, now you're adding mass, whether it be via speed differences or whether it be directional differences. Whether it be confluence or speed convergence, guess what's happening here? We're adding mass in the upper troposphere. As the air converges, that mass is added. The addition of the mass to the vertical column produces higher pressure at the surface because as that upper level convergence, the air streams meet, the air currents meet, the air must eventually go down and sinking vertical motion occurs. As the air sinks, it eventually hits the Earth's surface, and as it presses on the Earth's surface, your surface pressure is getting higher because pressure is simply force per unit area. So we have downward vertical motion pressing on the Earth's surface, causing that barometer to go up. You get rising pressure, which then initiates. Once that downward vertical motion, that downward air streams hit the Earth's surface, they spread out, which is known as horizontal divergence of the surface, which is associated with higher surface pressure and nice weather. So there's your DVM, downward vertical motion, or sinking air motion. As air sinks in the atmosphere, it's going to warm adiabatically due to compression, and the possible cloud and storm dissipation occurs. You want rising air motion and adiabatic cooling to get clouds and storms. In this case, we have adiabatic warming and sinking air, and we have associated improving weather and stability is increasing, it's getting better. Here's a diagram of the damper effect. Damper effect means good weather. Convergence aloft, in this case, it's due to speed differences. I have a 50 knot wind to the upper right portion of the diagram at the top, and I have it's a 95 knot wind blowing toward a 50 knot wind. Just think about this. If you're driving 95 miles per hour and the person ahead of you on the interstate is only driving 50, eventually you're going to catch up to that person. So that line of cars is going to get longer. You're adding a line of cars, it's getting longer. In the atmosphere, now we have 95 knot winds blowing into 50 knot winds. Well, guess what? Eventually, the air is going to collide with the air ahead of it, and the air is going to want to sink as a result. Those arrows are pointing downward in this case from the upper troposphere. And then eventually the air spreads apart and via divergence at the Earth's surface. So this is associated with high pressure. Sinking vertical air motion, high pressure, good weather, damper effect. And then the chimney effect is rising air motion, cooling, clouds and storm development with the chimney effect. Here's an example of if we had a condition in which we have confluence, where these dashed lines at the very top portion of the diagram are coming together along a common axis point. So we have confluence, or air converging via wind direction. As air converges in the upper levels of the troposphere, mass is added. The continuity, mass continuity, remember that whole concept with mass continuity. If I'm adding mass to the upper levels of the atmosphere, it's got to go somewhere. It's got to be redistributed throughout the atmosphere over a larger area. And so therefore I have downward vertical motion. As the air sinks, it warms, it dries out. Mostly clear skies occur as a result, and you get lighter winds at the surface associated with surface high pressure. Beautiful weather. These are some of the better weather days you'll ever experience at the ground. The nice sunny, very blue skies, crystal blue skies on days in which we have downward vertical motion and surface high pressure. Now with mass continuity, if we conserve mass, whether we lose mass or gain mass, whether that mass is redistributed or it comes from some other location in the surrounding atmosphere, there's something known as a level of non-divergence, and this is represented by the letters L and D. Convergence or divergence aloft results in the opposite effect in the lower troposphere. So this is the cool thing, right? The level of non-divergence, I'm going to show you a diagram here in a minute. That's the level of the atmosphere. It's usually in the mid-levels where convergence and divergence flip-flop or change. So let's say you have upper-level convergence above the L and D, or addition of mass. Below the L and D, it's going to be the opposite effect. Opposite of convergence is divergence. Or let's say you have divergence in the upper levels of the troposphere above L and D. Below it, you're going to have convergence. So it's that line that delineates convergence versus divergence in the atmosphere. That's the L and D. There must exist at some level in the atmosphere a level of non-divergence. Few facts about the L and D. It's found under average conditions. I mentioned this over in the middle atmosphere, middle portions of the atmosphere, around 600 millibars, but can vary between 700 and 400 millibars. 700 millibars is about 10,000 feet above the ground level. 500 millibars is 18,000 feet. So if it's 600 millibars, I'm basically going to be looking at somewhere around 13 to 14,000 feet above the ground is where you're going to find that level of non-divergence typically. It marks the level of transition from convergence to divergence or vice versa. The height will be highly variable, and it's going to be based on the atmospheric situation. For example, that level of non-divergence, L and D, is found at higher heights as the system's developing, the early stages of development and intensification. And it's responsible for steering baroclinic lows and highs. We talked in the last training session on the difference between baroclinic and barotropic, remembering that baroclinic is associated with mid-latitude systems here in the United States and changes in air masses for sure. Fronts, low and high pressure systems, vorticity is all associated with baroclinic systems in the atmosphere. Here is an example of the 3D effects of the chimney and the damper effect. The portion on the left is showing the chimney effect. You see on the vertical axis, I have labeled the different levels in the atmosphere. 850 millibars is about 5,000 feet above the ground. 700 millibars is 10,000 feet above the ground. Then you have that LND, that level of non-divergence, was situated between 700 and 500 millibars. You see the LND line marked. We all are operating in that tropospheric layer, the layer which you're most familiar with, that has all the weather. 500 millibars is above that LND. That's about 18,000 feet above the ground. 300 millibars is above that, up at about 30,000 feet, jet stream level. And then 200 millibars is at 40,000 feet approximately in the atmosphere. Okay, so with the chimney effect, the white arrows on the left show upward rising air motion. You see convergence of air at the lower levels of the atmosphere, right where that word chimney is on the bottom there, bottom left, chimney. See those white arrows, how they're basically pointing towards each other, and then basically the air rises as a result of that low level convergence. So in the case on the left with the chimney effect, I have convergence below the LND. Above that, you'll notice I have the spreading apart of those white arrows at about 300 millibars, 30,000 feet, and that is my divergence, my upper level divergence with the chimney. Upper level divergence aloft, low level convergence below it in the lower troposphere. And so opposite effects, convergence with the chimney effect below the LND, divergence above it. So the LND is your transition between the low level convergence and the upper level divergence in this case. And usually above the chimney effect, where that air is spreading apart in the upper atmosphere, you have a sinking air from the stratosphere that comes down, and this is known as a warm sink. So there's warmer air from the stratosphere that actually gets injected downward. It's trying to replace the mass that's lost. So that warmer air from the stratosphere actually works its way downward in the upper troposphere. It's known as a warm sink. The image on the portion on the right shows the damper effect, and it's just the opposite. You have air in the upper troposphere above 300 millibars in this case. The arrows are pointed towards each other, those white arrows, and that's upper level convergence. As the air converges, it's got to go somewhere, so it sinks. See the downward directed white arrows? Sinking air motion dries out the atmosphere. Clouds dissipate and usually have high pressure. Once that air gets to the surface, though, it spreads out horizontally away from each other. That's known as low level divergence. So with the level of non-divergence, notice it's a little bit higher in the case of the damper effect where the air is sinking, because the air is warming as it sinks. And you get what's known as a colder cold dome, colder air. You get this mass or upper level convergence and the damper effect. You get this air that bulges up higher, and you get colder air from the troposphere, which shoots into the lower stratosphere in this case. You can also see how that height of the troposphere varies based on whether you have sinking air or rising air, chimney versus the damper effect. So this is a great diagram that really breaks it down. You see where that LND is, the level of non-divergence. It's between 700 and 500 millibars on average, between 10,000 and 18,000 feet. This has huge implications for the weather we experience here at the surface, the vertical air motions. All right, so processes that generate horizontal divergence and convergence. In the upper levels, we have something that's known as a gradient wind, which produces divergence and convergence associated with atmospheric waves. Generally for the same pressure gradient or height gradient and at the same latitude. So we're basically saying the pressure gradient or the height gradient is the same. Gradient winds will generally be stronger in anticyclonic curvature or ridges, the long wave ridges at the jet stream level. You have gradient winds which will be stronger in those ridges or anticyclonic curvature. Gradient winds will be weaker in those troughs, those long wave troughs. In general, those gradient winds are slower, okay? In cyclonic curvature in the long wave troughs. These supergeostrophic and subgeostrophic winds develop as a result. Okay, so you get these gradient winds. Realize that the gradient winds are stronger in ridges, upper level ridges at the jet stream level. They're slower. Those winds are much slower or weaker in cyclonic curvature in the troughs. And as a result, you get these areas in the long waves that are either supergeostrophic or subgeostrophic. They generally develop supergeostrophic occurs within the anticyclonically curved flow around upper level highs or ridges, and the subgeostrophic flow is going to develop in the long wave troughs. These troughs and ridges make up an upper tropospheric wave pattern within the jet stream. These are your long waves. I talked a lot about long waves and short waves. We talked about atmospheric waves in the last training video. You have this acceleration and this deceleration, speeding up or slowing down of the actual winds within this wave pattern, which generate regions of upper tropospheric divergence and convergence between troughs and ridges. And I'm going to show you a great diagram here in a minute. Hang tight, we get through these words, through all these statements here. Generally, downstream of a trough and upstream of a ridge, the wind undergoes speed divergence as it changes from a cyclonic to an anticyclonic curvature. That's going to undergo the air undergoes required acceleration or speeding up from a subgeostrophic state to a supergeostrophic state. On the other hand, conversely, upstream of a trough and downstream of a ridge, the wind undergoes speed convergence as it changes from anticyclonic, the ridge, into a trough, cyclonic curvature. And if you are going to have speed convergence, you're adding mass in the upper levels of the air and you have sinking air motion, right? So let's take a look at this. This is a really good diagram. We're looking at the jet stream level here. I want you to imagine this blue shaded line, this whole blue shaded line is the thicker blue shaded line. That represents your jet stream axis, right? The oval areas here with the dashed lines around them, those represent what we were just talking about on the previous slide, okay? Think about this. If you're pedaling on a bike and you're coming up on a big hill, you're pedaling uphill, it's going to be painful, right? If you're ever pedaling a bike, you always want to take a hill going down, not up. If you had a choice between going uphill or downhill and you're pedaling a bike, you would most likely pick downhill because it requires much less energy and effort on your part. The same thing happens in the atmosphere as these air parcels move up into this ridge, right? As they move upward into the ridge in the upper left-hand portion of the diagram, the air parcels are going to speed up. If you're pedaling a bike uphill, you're going to want to pedal as quick as you can so you can just get the pain over with, right? You don't want to be pedaling slow. You want to pedal quicker and move faster to try to get to the top of that hill as quick as you can so you get that pain over with. You don't have to use as much energy once you get to the top of the hill, right? Same thing goes in the atmosphere here. These air parcels are going to speed up as they come into a ridge. As they go across the top of this ridge or this area of higher atmospheric heights, this huge hill in the atmosphere, that's called supergeostrophic winds. Remember, super means faster or higher wind speeds. So as the air parcels then spill over the top of that ridge, they run into an area of speed convergence because what's happening is, let's just say you're on that bike over the top of the hill and now you're starting to come downhill, right? You're going to be going fairly quick. So with speed convergence, they're basically to the east of the ridge axis, in this case, downstream of the ridge or upstream of the trough. There's speed convergence, and with speed convergence, you're adding mass in the upper troposphere. As you add the mass, the air must sink vertically, air sinks, and then it spreads out horizontally, diverges at the surface. So areas of speed convergence in this jet stream are in this general position, downstream of the ridge axis or upstream of the trough axis. And the speed convergence area represents downward vertical motion, sinking air, and high pressure and nice weather. Notice what happens as these arrows, you go down through the trough. You got this long wave trough at the jet stream level. The wind speeds slow down as you get to the base of this hill, the bottom of the hill. Let's say you're coming down the hill on your bike now and you're really moving fast, going downhill, and you see a car ahead. There's a stop sign for you as you're coming down that hill. You slow down to avoid basically riding out in front of that car. The same thing applies to the air parcels in the atmosphere. Not as much energy is required as the air parcels come down into the base of this trough, so therefore they slow down or decelerate. And that results in a sub-geostrophic wind in the base of the trough. Sub meaning slower, slower wind speeds, lower wind speeds. Once the air parcels come out of the trough and start moving back up into the supergeostrophic winds of the ridge downstream, you have an area of speed divergence. And so this is the case again at which your air parcels are speeding up. They're speeding up. They're going up a hill again, so they're trying to get that pain over with. And it's a lot of energy and a lot of effort by these air parcels. It requires a lot of atmospheric energy. As a result, the air moves up and accelerates over the top of that hill. And that's a supergeostrophic wind at the top of the ridge again. So the conversion from subgeostrophic in the trough to supergeostrophic in the ridge results in an area of speed divergence. And with an area of speed divergence, the air wants to rise in the vertical, clouds form, adiabatic cooling happens, you get storm development. In the area, that's that oval area there with the dark hashed line around it, that's an area of speed divergence in the jet stream. That's a favorable area for low pressure to develop. So these convergent and divergent patterns between the upper level troughs and those ridges force vertical motion in the mid-troposphere, and that results in pressure changes at the Earth's surface, lowering surface pressure in an area where there's speed divergence, and increasing surface pressure in the area where there's speed convergence. The upper level divergence downstream of the trough and upstream of the ridge is going to result in lifting through that level of non-divergence. It's going to generate your clouds and possible precipitation. The surface pressure will fall. You'll notice your barometer will have a falling tendency. It's going to generate regions of low pressure and converging winds right in the speed divergence area. So you notice how your arrows, your big arrows here on this diagram, they represent your wind flow through the main jet stream axis. And so as you go out of the trough, see how the arrows are pointing up out of the trough? That's showing an area of speed divergence. That's what we were talking about on the next slide, this slide here. You got rising air motion and most likely storm development in that speed divergence area. Because divergence, again, is the removal of mass aloft, so the air from below must converge and come up, rise vertically to replace that mass aloft. On the other hand, the upper level convergence downstream of the ridge and upstream of that trough axis forces mid-tropospheric air to sink through that level of non-divergence, L and D. That's going to generate clear skies and dry conditions. And in this case, surface pressure rises, generating regions of high pressure and diverging winds. So the area where there's speed convergence there, faster moving winds are blowing into slower moving winds ahead of it. That's going to result in a piling up of air in the upper levels of the atmosphere and the troposphere. And that's going to result in sinking air motion and surface high pressure and nice weather. And there you go. This shows you where areas of high pressure favored based on the speed convergence. That's where the H is at. And then the L, the low pressure at the surface, is created by regions of lifting and associated with speed divergence. And so these are the positions within the jet stream. How would you apply this? You would look at the jet stream and you would look for regions of super and subgeostrophic flow. You look for those super and subgradient winds. You would look for jet maxes, which are accelerated areas within the jet core. They would result in rising and sinking air motions, high and low pressure respectively at the surface. Right, so with jet maximum, keep in mind, these jet streaks, these faster moving areas within the jet core or jet axis are located near the tropopause. You get strong divergent and convergent patterns that are produced by these. When we're talking about jet maxes or jet streaks, we're talking about areas where the wind is rapidly increasing or decreasing. And we call these super and subgradient winds at the jet stream maxima with those jet stream maxes. This results in the temporarily out of balance situation in the ageostrophic winds and results in a convergence and divergent patterns produced by changes in the height gradient near the jet streaks. So when we talk about jet maxes within the jet stream, I want you to think about the gradient winds. Sub again meaning lower or slower winds within the jet max entrance region. And I'll show you what this looks like here in a minute on a graph. When you first enter the jet max entrance region, Your height contours are getting closer together, your lines of equal height, but the wind has not yet responded. So the actual wind is slower or subgradient, weaker than the tightening contour gradient supports when you're entering the jet max entrance region. It's called subgradient wind. Here's an example of a subgradient wind showing the purple box here represents the air parcel. A geostrophic wind is created. Keep in mind, a geostrophic wind is when these forces are out of balance. In this case, at the jet stream level, when we're talking about jet maxes or accelerated regions of fast-moving air within the jet axis, at the point on the far left, we have the HGF, height gradient force. The COF stands for Coriolis force. And the V sub G, the VG, that represents your geostrophic wind. Geostrophic simply means the wind is blowing parallel, perfectly parallel to the height contours. But with a height gradient force, it's going to be directed from higher toward lower heights. So I have 558 decameters at the bottom, I have 552 decameters at the top. Height gradient force is directed from higher toward lower heights. That's why it's pointing up in this particular case in the far left. The air parcel is represented by that purple cube. Okay. The Coriolis force is always going to act to the right of the wind direction in the northern hemisphere. It's the apparent force, deflection to the right in the northern hemisphere. These are both an equal and opposite direction, or the equal magnitude. Equal and opposite magnitude at the air parcel on the far left. No problem. Everything's happy, geostrophic wind flow, complete balance of forces here. Now, as that parcel gets closer to this jet max entrance region, you'll notice the solid black lines are getting closer, they're getting more closely spaced, or they're tightening up in spacing. So that's going to result in a stronger Coriolis force, COF, a stronger pull of mass to the right of the air parcel. That's going to result in what's known as a subgradient wind. That middle air parcel there represents a subgradient wind because your Coriolis force, there's ageostrophic flow here with subgradient winds because your Coriolis force temporarily is stronger than the HGF, the height gradient force, at the middle point. And then once that parcel gets back into the middle of the jet max, gets beyond that jet max entrance region, gets in the middle of the jet max, we have a VG again, a geostrophic wind, which blows perfectly parallel to the height contours, and you notice things are back in balance. The HGF height gradient force is pointing from high to lower heights. It's equal and opposite in direction to that Coriolis force, which is acting to the right of the air parcel's motion. So this is the case of subgradient winds. You get these in the entrance region of jet maxes. Things initially are in balance. They're geostrophic between height gradient force and Coriolis force. Then they temporarily go out of balance in the jet max entrance region where the Coriolis force is temporarily stronger than the height gradient force. That's known as a subgradient wind, slower wind speeds temporarily. Then that parcel eventually speeds up in the middle of the jet max, and you have balance again established in a geostrophic wind. So that jet entrance region is characterized by confluence in the height contour pattern. You see how these solid black lines are getting closer together. So that represents confluence, or the coming together of the height contours, which results in additional mass in the upper levels of the atmosphere. The subgradient winds are in the process of speeding up or accelerating in this case. And whenever that happens, the potential energy of stored position is converted to kinetic energy, the energy of motion, as subgradient winds turn downhill and they accelerate towards lower heights. So in this case, the potential energy is decreasing. That kinetic energy or energy of motion in the form of wind speed is increasing. So again, subgradient winds are deflected to the left of the gradient flow. Just realize again how things are not in balance until you get into the middle of that jet max or the jet streak. Height gradient force and Coriolis force eventually become reestablished with balance, and we get that geostrophic wind again at the middle portion of the jet streak or jet max. And while the winds are subgradient, they will deflect toward the left, favoring the stronger height gradient force. And then height gradient and Coriolis force are out of balance, so that's an ageostrophic wind component, where we got height gradient force exceeding Coriolis, and thus we get an ageostrophic wind development. Okay. Here's the example of the jet max, right in the heart of the jet core. It looks like a football, doesn't it? The shape, this blue area. The area on the left, when that parcel first comes into the jet max, which is this football shaped pattern, that's known as the jet max entrance region. The area on the right, where that air parcel goes out of the jet max, is known as the exit region. You get ageostrophic wind components created at both the entrance and exit region due to speeding of the air parcels into the jet core, to the jet max, and then a decelerating or slowing down to the right. Image courtesy of the COMET program. And then lastly, we have what's known as super gradient winds. Super, again, being faster or stronger within the jet stream exit region. Winds in the jet exit region are adjusting to a rapid decrease in the height gradient force. So we have a height contour starting to spread apart again and get much further apart from each other. So the actual wind is faster or stronger than the weakening gradient supports. So now with the super gradient wind out at the jet max exit region, see how the solid dark lines are getting further apart here? That's spreading apart due to diffluence. And so again, let's look at the image on the left, the purple cube. That purple box represents the air parcel. Perfect balance between height gradient force and the Coriolis force initially, but as that air parcel comes out of that jet max exit region, the height contour spread further apart, which makes a case where we have the height gradient force is temporarily stronger than the Coriolis force, and therefore mass is going to be deflected. So with the jet exit region is characterized by diffluence or spreading apart of the height contours. It's a relaxing of the height gradient. Super gradient winds are in the process of slowing down or decelerating. And then we have kinetic energy, which is being converted to potential energy. So energy in motion, as the parcel slows, kinetic energy decreases. Potential energy increases as super gradient winds turn uphill and slow down toward higher heights. So if we deflect things to the right of motion, the height gradient force weakens immediately upon entering the diffluent height contour area. So we have the height gradient force becoming weaker than the Coriolis force. So everything is being pulled, mass is being pulled to the right while the winds are super gradient. Everything deflects toward the right, toward higher heights, favoring the stronger Coriolis force. And again, ageostrophic flow occurs temporarily as that air parcel comes out of the jet max exit region. Why is this important? Why is all this important? Because we have areas of upper level convergence and upper level divergence, which impact rising and sinking air motions in the atmosphere, nice high pressure areas of the surface, or storm systems of the surface. In the jet max entrance region, you have a direct circulation, and in the jet max exit region, you have an indirect circulation. And you see the boxes below the jet max itself, and it shows you where you have CON represents upper level convergence, DIV represents upper level divergence. So you see how everything is linked between the lower atmosphere all the way up to the jet stream, to this jet max? See how you have rising air motion, warmer air and rising air motion when you have upper level divergence, and then you have sinking air and sinking colder air when you have upper level convergence. In this case, in that jet max entrance region. And then you notice you have divergence and convergence with that jet max. See the circulation in the box below that. So if you're located, you look at a 300 millibar chart, jet stream chart, look for these areas of higher wind speeds known as jet max embedded within the jet axis. If you're located below the DIV, the upper level divergent quadrant, the left front and the right rear in this case, you're most likely going to have rising air motion and possible storm development. Whereas if you're located below the CONV, upper level convergent areas, that results in sinking air motion, usually fair weather. So it's very important that you take a look at the circulation. Now, what we just looked at, that is a case where we're assuming straight line flow. In a lot of cases with the jet stream, we have high curvature areas, strong curvature areas and troughs and upper level ridges in that jet stream pattern. So in that case, you have a gradient wind relationship which complicates those divergent patterns. Now, with frictional effects near the surface in the low levels, within that planetary boundary layer, friction is going to slow the wind speed down, and as a result, it's going to disrupt the geostrophic balance of forces, and it's going to create that out of balance flow, that ageostrophic flow, because as wind blows across the ground, it slows, but it also gets turned across the isobars towards lower pressures. In cyclonic flow around surface lows, friction induces mass convergence. So when you get a very strong developing storm system, you get a very strong pressure gradient, very strong wind speeds, eventually friction is going to take its toll on that storm system. It's eventually going to act as a braking mechanism and slow the pressure drop, the pressure fall, or actually cause it to start rising and that pressure to fill in that surface low. So friction acts to add mass in the low levels of the troposphere near the ground. This is going to force lifting of the air. In the beginning stages of storm development, this lifting actually helps enhance cloudiness and precip in the vicinity of surface lows. Whereas around high pressure systems, surface highs with anticyclonic flow, friction is going to induce mass divergence. And that near surface divergent forces sinking of the air from above. And anytime you have air in the atmosphere vertically sinking, this helps evaporate clouds and aids in generation of clear, dry conditions. So there's your surface high and surface low. You notice the flow around high pressure in the northern hemisphere is clockwise, as indicated on the right by those black arrows, outward and away from the high pressure center. You get what's known as friction-induced divergence. On the image, the left-hand portion of the image, with the low pressure system at the surface, air blows counterclockwise in the northern hemisphere around low pressure and generally inward towards the center of that low, where you get friction-induced convergence of cyclonic flow. So this results in convergence into the surface lows and divergence out of surface highs. Okay, and we're almost wrapped up now. Just a couple more points on tonight's training. In the upper levels, the gradient wind relationship produces divergence and convergence associated with atmospheric waves. Near the tropopause, we get these strong divergence and convergence patterns produced by jet stream maxima. So above the tropopause, once again, we get changes in the height of the troposphere caused by replacement and displacement of mass. This is resulting in those warm sinks and those cold domes we talked about. They're found above the tropopause in the stratosphere. So warm sinks and cold domes. With warm sinks, again, just realize these are warm pockets of stratospheric air that are evident on the 200 millibar chart. 200 millibars is up at about 40,000 feet above the ground. And warm sinks are found above strong upper level divergence, which causes the height of the tropopause to sink with respect to the 200 millibar surface. So generally associated with your chimney. Warm sinks are associated with the chimney effect. Upper level divergence removes mass. Air from above that point in the upper troposphere sinks from the stratosphere. That's known as a warm sink. Cold domes, on the other hand, these cold pockets of tropospheric air that are evident on the 200 millibar chart at 40,000 feet, found above strong upper level convergence, which causes the height of the tropopause to rise with respect to the 200 millibar surface. So cold domes are associated with your damper effect, where you have strong upper level convergence or the addition of mass, sinking air motion from there, cold domes occur. And there it is once again. I already really explained this pretty well, so I'm not going to harp up on it too much more. I explained about this earlier in the training session, but just again shows the warm sinks. Generally from the stratosphere, that warmer air comes down into the upper troposphere in an area where you have upper level divergence, the chimney effect, the colder dome associated with the damper effect where you have upper level convergence, the sinking air motion. All right, that wraps things up tonight. Spot on weather. It was a little lengthy. I tried my best to push through these training sessions so it's not too lengthy. But in general, this was a great training session tonight. We talked about atmospheric motions. Very important. Very important, because this atmospheric motion results in rising and sinking air in the atmosphere, which ultimately leads to high and low pressure systems at the surface. So we have to look again at the atmosphere in 3 dimensions. It's not a 2-dimensional flat plane surface, it's a 3-dimensional fluid. So we need to look at longer waves, kind of how they tie in with favorable areas of storm development, high pressure development, stormy versus nice weather based on divergence and convergence in the upper atmosphere, speed and directional in nature. All right, that wraps things up. We got a lot more to cover this summer. You know, we're looking middle July right now. We're right on track. Keep it tuned to Spot on Weather. Not really been doing any videos lately on weather per se during the summer. We're pretty much locked into a hot, sticky, humid pattern right now across the east. You know, Tropical Storm Barry became Hurricane Barry, moved into Louisiana today on July the 13th, 2019, producing a lot of rain down there in Louisiana. So could be some flooding down in the deep south. All right, that wraps things up. If something exciting happens with the weather, I'll be making some weather forecast videos. But right now, sticking to the training, summer training. So glad you watched, and thank you so much for subscribing to the Spot on Weather channel. Don't forget to follow us on Facebook as well as Twitter. Follow us with the local forecasts for Southeast Virginia. That wraps things up on Spot on Weather tonight. We're Spot on Weather. If we're not spot on, we're not doing it right. Have a super night, everybody. Take care. Until next time.